Okay. Okay. Record. Oh, I should have asked. People on Zoom, can you hear me? Can you write in the chat if you can hear me? Yes, perfect. All right. Okay, I got some demos to go along with chapters 15 and 16, so I guess I should ask, what chapter do you want to start with? 14, 15, 16? Okay, yeah, there's just like a couple of things for 14, so why don't we just get 14 out of the way, and then we can do some cool demos? Okay, all right. So chapter 14, the only thing that will be assessed on midterm 2 is mechanisms and catalysis. So mechanisms is the last way to get a rate law, and what a mechanism is built upon is the idea that this is kind of like our guess at how the atoms and particles are interacting and colliding with one another in space to yield a net chemical reaction. So mechanisms can be more than one step. Oftentimes they are multi-step. And so how we approach rate laws is we always look for the rate determining step. So the slowest step is always the rate determining step that dictates our rate law. The fun thing about mechanisms is it's like a little puzzle, is that finally, we are allowed to take the stoichiometry from the reaction and turn that into the exponents in your rate law. So let's just go through, I think there's like 2 or 3 questions here or something. Okay, here's a reaction. Ozone in the upper atmosphere is destroyed by this 2-step mechanism. So notice these are just 2 different steps and they add up to an overall reaction. So what we can do is just add up these 2 steps, kind of like Hess's law, see what cancels out in our reaction. So what we're looking for are things that are produced and then consumed in subsequent steps. So if you look closely here, what are some things that cancel? CLO cancels, so that doesn't show up in our overall reaction. Is there anything else that cancels? Cl, yes, notice that the Cl also cancels, but it cancels a little bit differently, and notice how I changed the color here. So let's just get the overall equation, where now I don't write those things that I've canceled out, so it looks like it's simply O3 plus O. All of these are gases, I just don't feel like writing it. 2 O2s, right? And so the follow-up question here is identify catalysts and identify intermediates. So the things that we canceled out in our reaction are actually our catalysts and intermediates. It's just be careful of differentiating these. Catalysts, these are consumed and then they are produced in a reaction. So you will find them in order. You will find them as a reactant first, then a product. And then intermediates, on the other hand, they are produced and then consumed, then consumed in a multi-stepped mechanism. So you'll find it as a product and then a reactant. So if we go back to our actual process here, CLO would be what? A catalyst or an intermediate? 50-50. It's an intermediate because it is made in the first step and then consumed in the second step. So it's basically made like during the process and then consumed before the reaction is over. So CLO is an intermediate. It's not something we actually add to the reaction. It's just kind of like part of the process for this chemical reaction. So CLO is an intermediate, and then therefore Cl is a catalyst. We actually have to add this thing to our reaction. Technically, you know, we add it along with our reactants, but it doesn't show up in the overall equation because it's produced at the end and basically regenerated. So yeah, so that's how you dictate or figure out what's a catalyst, what's an intermediate. Intermediates always produced, then consumed. Catalysts have to be added at the beginning, and then they're regenerated at the end, but both get canceled out of the chemical equation. All right, so there's that. That kind of has to do with catalysts too, the next section of chapter 14. This question is about now mechanisms, the rate determining step. The slowest step dictates your overall chemical reaction. We're still working with ozone. But here I give different mechanisms on how an overall reaction can occur. I will point out that on exams, we will never ask you to write a mechanism from scratch. Typically what we do are things like this. We give you the steps. We tell you which one is slow or something, and then you give us the rate law. Or maybe we give you 3 steps, and you have to determine which is the slow step that matches a rate law. So that would require you to go through, okay, ask yourself, what if the first step is the slow step? What if the second step is the slow step? What if the third? We'll never ask you to actually conjure up a mechanism on your own. We'll usually, like this, like in this example, give it to you. So here I have a 2-step mechanism, and we're just going to approach it, okay, what if the first step is the slow step? What if the second step is the slow step? What are the subsequent rate laws for those? So, you know, we already did rate laws with the integrated rate laws. We already did the method of initial rates. With mechanisms, we simply take the slowest step, and the reactants in the slowest step dictate the rate law. That's it. So, but we got to be careful. So if this first one, where the first step is the slow step, this one's easy. The rate of this first step is equal to the rate constant for that first step times the concentration of the reactant to the first power. That's it, right? So the first step dictates, the slowest step here dictates the overall rate of the reaction, because the assumption is that this first step is slow, so slow, but as soon as it's done, the fast step takes over and the reaction's done. So that first step dictates the overall rate of this reaction. So notice that the stoichiometry here and the reactants became the exponents in my rate law. So for example, if there was a 2 stoichiometry here, there would be a 2 exponent order there within the rate law, if there was stoichiometry, but in this case, there's not. So there is the first rate law. If the first step is the slow step, that one's the easy one. The follow-up here is, okay, well, what if the first step isn't the slow step? What if it's the second step instead? So this one's just a little bit trickier, but not so bad. We still use the same idea that the slow step is the rate determining step. That is what dictates our rate law. So we take the reactants of our second step and simply write rate equals the rate constant for that second step. So I'll just put K2. O concentration, O3 concentration. All right, can I put my hands up and say I'm done? Nope, what's wrong here? We can't have an intermediate, yeah, so we can't have that O in there because we never add it to the reaction. So our trick to getting rid of it is we're gonna use the fast step. We're gonna use the fast step and recognize that this is a chemical equilibrium, which we'll talk about in a second. So what we'll say is that the rate of the forward reaction is equal to the rate of the reverse reaction for that first step. You don't actually have to do what I'm showing right now. I just want to be comprehensive here. So that we have the forward and the reverse rate are equal to one another. That's the definition of chemical equilibrium. So we can write the forward rate law, K1 O3 concentration equals K -1 O2 concentration O concentration. So what I want to do is isolate O in terms of things that we know, so then I can replace that O in our original rate determining step with other concentrations. So I'm just gonna move some stuff around here, and what I see is that the O intermediate concentration is equal to K1 over K -1, which is just a overall K, O3, O2. And so what's really important here is this O3, O2 ratio. This is what's going to replace that O intermediate in our original rate determining step rate law. Don't freak out that there is something in the denominator. Just replace the thing that we're trying to replace here, which is this intermediate. Just replace it with that whole thing. And so when you do that, when you do the replacing, you get that the rate law here is rate equals, I'm just going to say K overall, There's 2 O3, so it's O3 squared, so second order, but then O2 in the denominator, right? So here we have a reaction that's second order with respect to ozone, but then a -1 order with respect to oxygen, right? So there is our rate law. All right, so any questions about the slow step being the second step? Yeah. Yeah, so the question is, what if, can we have a catalyst in our slow step? So notice that we had to use the fast first step to get rid of an intermediate. We cannot have intermediates, but we can have catalysts. The reason is because in an intermediate, you don't ever add to the reaction. You never make it. It is made in the reaction and then goes away by the end. But if we go back to like this question, catalysts, you actually do have to add them to our reaction. So if a catalyst shows up in the rate law, that's absolutely okay, right? Just no intermediates. Question? Wait, up? Down. Okay, all right. Okay, all right, so good with slow step, second step. So the idea here is if you have an intermediate in your second or even third step, we're going to use the fast equilibrium steps prior to get rid of any intermediates. Okay, all right, here, okay, consider, okay, was this chapter 1 or midterm 1? I'm not sure. All right, let's just look at this reaction. Okay, we have a reaction. A plus B goes to C, where the rate law is rate equals the rate constant times the concentration of A squared. So it looks like this is a second order reaction. Okay, so indicate whether the following statements are true or false. You know, half of this question is actually midterm 1, but I think this question scored very poorly on the midterm, so it's probably good to go over it. All right, increasing the initial A concentration will increase the overall rate and the rate constant for this reaction. True or false? False. What makes this false? Remember what rate is. Rate is this guy. Rate constant is K. The only thing that affects K is the Arrhenius equation. K equals A, e to the negative EA over RT. So if I increase the A concentration, yes, the reaction goes faster, rate goes up, but not because K increases. So this first one is false, and the reason is because K does not change. K is not affected. Increasing concentrations or whatever has no effect on the rate constant, but it does have an effect on the rate. Okay, next one. Increasing the initial B concentration will increase the overall rate and the rate constant. True or false? Yeah, super false. Will B change the rate constant? Will B change the rate? No, why? Why? It's not in the rate law. Yeah, very good. So here B is 0th order, so it's actually gonna have no effect on any of those things. All right, so it seems like B isn't in the rate determining step. It's in the fast step probably. All right, increasing the temperature will increase the overall rate and the rate constant. True or false? Yes, this one is true because when you increase temperature, the value of K increases. The reason? The Arrhenius equation. All right. And then, so if K increases, remember K is in our rate law, then also rate will increase. So I was able to make this reaction go faster without changing any concentrations at all. Increasing the temperature increases K, which then increases rate, versus increasing concentrations, just increase rate, has no effect on K. And then finally, introducing an effective catalyst will increase the overall rate and rate constant. True or false? So what does a catalyst do? It lowers your activation energy. So if my reaction was initially like this, what a catalyst does is give a different pathway to make the route a little bit easier. So the difference between these two reaction coordinates is that the hill is a different height. So what do we call this hill that reactants have to get over to get to products? Activation energy. So does activation energy have an effect on rate constant? Yes. And so what we see here is that an effective catalyst will lower your activation energy. Therefore, will increase K, your rate constant. So will your reaction go faster? Yes, it will. All right. So the catalyst is kind of like temperature in a way where it affects the rate constant, therefore affects rate without changing any concentrations or anything. So the first two are false, the second two are true. The first three are kind of like review from midterm 1, but the new idea here is that last piece. Okay, all right. So chapter 14, done. All right, what do we want to do next? Just keep going, 15? Okay, let's just go in order. All right, I don't want to do my demo yet. We'll do it later. Okay, so chemical equilibrium. So when we were talking about rate constant, K, that's what I call little k, rate constant. That's related to rate laws. But equilibrium constant, that's big K, right? Big K describes a scenario where your product and reactant concentrations remain steady, remain equal at a very stable condition. And how we tell the reader what is the ratio of products versus reactants is we use the ratio big K, equilibrium constant, to say about how much product, about how much reactant is there when we establish chemical equilibrium. So something that's very helpful is to understand that big K is very generally product concentration over reactant concentration with appropriate exponents, meaning that anything that has stoichiometry in your chemical equilibrium becomes exponents in your K expression. So just based upon the magnitude of K, we can tell what's present at equilibrium. If K is really big, think about how can you make a fraction a big number? You can have a lot of products, or you can have like a very, very, very small amount of reactants. Having a big number in the numerator or a very small number in the denominator yields you a really large K value. Versus a small K value means that you have a lot of reactants present and not a lot of products present. So just that magnitude kind of tells you something about that reaction, right? Is that K1 times K over -1? I didn't answer that question. Oh, these Ks, K overall, it all kind of just went away. All these Ks combine, and so we can't really, in a mechanism, distinguish between K1, -1, and 2. We just observe it as one overall K, so that's why I just write K overall. All right, sorry, I forgot to answer that. Okay, all right, so here I give you some concentrations at equilibrium, and I give you the equilibrium reaction. So a couple skills here. We need to be able to write our equilibrium expression. We have KPs and KCs. So notice in this question, I give a KC. C stands for what? Concentration. KP, P stands for what? Pressure. KW, W stands for what? Water. Yes. So we're gonna work with a lot of Ks, and there's like more to come. More Ks to come. Ks out the wazoo. So in this case, we give you Kc. So that means when we derive our K expression, we want to make sure we include things that have concentrations. Gases and aqueous things have concentrations, but when we do Kp and insert pressures, only gases have pressures. So if I'm given a Kc expression or value, I should write the expression so I know what that number represents. It's products over reactants of everything that has a concentration. Everything here is a gas. gases have concentrations. So this will simply be CH4 concentration times H2O concentration over H2 concentration, but this is to the third power, and then CO concentration. So notice that every stoichiometry, every coefficient became an exponent. Products over reactants. If I had a solid in here, would I include it? No, you wouldn't. Yes, so only things with concentrations or pressures. All right, so that's Kc. And I tell you that this value is equal to 3.93, right? K does not have a unit because it is understood that all the numbers inside here are either molarities or pressures. So when we report K, it's just a number of a magnitude with no unit. All right, so I tell you a bunch of information. I tell you we have a system at equilibrium. Here are a bunch of concentrations, and I ask you what is the methane, CH4 concentration at equilibrium. A common question in chapter 15 is, when do I have to use an ICE table and when do I not? So let me ask you, what does ICE stand for? Initial, change, equilibrium. Yes. So you need an ICE table when I give you initial conditions, and you need to figure out how the reaction has to change to get to equilibrium. In this question, I already give you equilibrium concentration. So do you need to use an ICE table? Nope, you just shove all those numbers into K and you're good, all right? So I give you K, I give you H2, I give you CO, I give you water. We are just solving for, okay, what does the number CH4 have to be in order for all of that to be equal to one another? So notice here, the key word, I don't want you to freak out on the exam thinking everything needs an ICE table. The key word is the system is already at equilibrium. So you are allowed to just shove it into the K expression. If I tell you initial stuff, you have to use an ICE table. Okay, so I'll just set this up real quick. So 3.93 equals, I'm gonna solve for methane. Water is given 0.0478 molarity. H2, 0.1566. Do not forget to cube it or you will be very sad. Then CO concentration, 1.5, or whatever that is, 1522, whatever. Okay. All right, and then just solve for methane. That is some number, I don't know. Okay, 0. Okay, CH4 concentration at equilibrium is 0.0481 molarity. My key doesn't have a concentration unit, but it's molarity. Okay, so key words, system at equilibrium means you put it right into K. All right, so we used Kc, so notice that everything has a molarity. So what is the Kp at this temperature? So let me just take a second and go to the very bottom and show you the supplemental information. This might be one of the only exams where you never actually look at the supplemental information because there's very little here. Really, the only useful equation is this Kp, Kc conversion and the quadratic equation solution. But there are tons of approximations that we can use, so we actually never really have to use the quadratic formula. So really, the only useful equation here is that Kp, Kc conversion. That allows us to convert between Kc and Kp, which is especially useful for all gas phase chemical equilibria. But recognize that gases have concentrations, all right? And so really what we're doing is the ideal gas law like a bunch of times to convert all the pressures to concentration. So when we use this Kp, Kc conversion equation, we need to know which R we use. Which one do we use? The 8.314 or the 0.0821 one? The 0.0821. Why? Because this second one concerns gases, but the 8.314, look at the units, joule per mole Kelvin. This one has to do with energy. So that the 8.314 version of R, That one is used for like the Arrhenius equation and those types of things where energy is involved. But for gases, you're going to use the ideal gas law version of R. All right, so you're going to use the 0.082 whatever number, and then therefore temperature should be in what unit? Kelvin, yes, like gas laws. Delta N is equal to the number of gases in your products minus the number of gases in your reactants. That is delta N. Products minus reactants, but only look at gases. Only look at gases. So let's use this equation to answer the question now. So, okay, what is Kp at this temperature? So Kp equals Kc RT delta N. I think I gave the temperature. I did. So T is equal to 1200. All right. We know the R we're going to use, so let's figure out what is delta N. This is how I approach it. I just count how many moles of gas are on our reactant side. 4 moles of gas. And then on my product side, 2. So that means delta N is equal to 2 minus 4. It is equal to -2. I lose 2 moles of gas in the course of this reaction. So putting everything together, Kp equals the Kc given, 3.93. RT, so 0.08206 times 1200 Kelvin delta N, so to the -2, right? So that's the process that you use there. Tricky with delta N, all right, and use the right version of R. And also don't, if there are solids involved, so if I had something like this, A solid goes to B solid plus C gas. Okay, what's delta N here? It is 1. It is 1. Why is it 1? Because I have 1 mole of gas on my product side and how many on my reactant side? 0. So it's 1 minus 0 in this case. But I guess 2 minus 1 would work too. But again, or if I had this, then here delta N would be 2. All right? That solids do not count, or liquids or anything aqueous does not count when you are calculating delta N. All right. Good. All right. Okay. So, all right, let's just keep going, I guess. All right, let's use this, use the following known equilibria, and then what is the Kc for this equilibrium? So the strategy here, it's like Hess's law, all right? Take the given reactions, manipulate them to make it match the target reaction, but the only difference is in Hess's law, we added the delta H's, but here with K's, when we add 2 reactions together, what do we do to their K's? Multiply them, yeah, so that's the only difference. So you want to ask yourself, what do I have to do these reactions to make them match? Look for the weird things and make it match. So here, HNO2, HNO2. Is that thing on the right side? Yes. Is it in the right number? Yes. So do I have to do anything to the reaction? No. So we're going to keep this one as is. All right. Next. What else is there? It looks like hydroxide. All right. Hydroxide's in that second reaction. So notice here, is the hydroxide in the given reaction on the right side? No. So we need to flip it. Is it in the right number? No. So what we got to do? Multiply by 2. And then that will make the 1/2 be 1, and then everything will be on the right side, and then we can add everything up. So that means when we manipulate these reactions, the first reaction just stays the same, 4.5 times 10 to the -4. But then the second reaction, we need to flip it so to the -1 and square it because we're flipping it. So we're going to take that number and take it to the -2. All right, so that 2 exponent is doing the doubling, the negative is doing the flipping. So that means this number is 1 times 10 to the -7, but that whole number is to the -2. So when we add these 2 reactions, we do not add the K's, we actually multiply everything together. So what we're going to put in our calculator is 4.5 E negative 4, 1E negative 7, caret negative 2. That is what you're going to put in your calculator, right? See, we're multiplying those k's together, and all the manipulations we do become exponents. All right, and so I think the number I get, the new k for this new reaction is 4.5 times 10 to the 10, I think. All right, okay, right, good. So apply Hess's law, but understand that the k's, you multiply them, and all the manipulations become exponents. Because remember with like enthalpies, if you flipped a reaction, you multiplied the enthalpy by -1. Here, we're taking those manipulations, making them exponents instead. All right. Okay. Ice tables, that's what you guys want, right? Yes. All right. So let's keep going. All right. So question 6. 1 mole of A is initially placed into a 2-liter container and then heated. Substance A decomposes by this reaction. At equilibrium, the concentration of B is blah. Calculate Kc at this temperature. Do I need an ice table? Yes, because I give you so much room. So you probably need an ice table. But what's the giveaway? Initially, okay? You place something in here first, and then sometime later you measure something else. That is the giveaway. You need an ice table. Ice tables, so what an ice table is actually a BCA table. It's a BCA table, but we just do something different with the after line. It's actually the equilibrium line, and that is what goes into our K expression. So we just need to be careful of what values we put where, all right? So in a BCA table, you always use the unit of moles, but in an ice table, you use the unit molarity or pressure. Since I want you to calculate Kc, what unit should I probably populate my ice table? Molarity, yes. So in the initial line under A, am I going to put a 1 here? No, because what is it? 1 mole is given. I want it to be molarity. So look, 1 mole, 2 liters. So what is the actual concentration of A? 0.5 molarity, all right? So if I only put A in the container, that implies there's nothing else. So 0, B, and C, right? So now we need to predict which way does this reaction have to go. It has to go forward. I'm really bad with my lefts and rights, so just say forward or reverse. So this reaction has to go forward because there's no products. It cannot go backwards. So what's going to happen is the change line is going to reflect the stoichiometry here. So we're going to lose a 2x amount of A. Why 2x? Because there's a 2 coefficient there. And then we're going to gain an x amount of B and an x amount of C. Right? So then at equilibrium, just like our BCA tables, you're just going to add up those columns. At equilibrium, you're going to find a 0.5 minus 2x amount of A, an x amount of B, and an x amount of C. The trick is for ice tables is your E line always goes into your K expression. So Kc is equal to B concentration, C concentration, A concentration squared. All right, that's a skill you need to be able to do. Look at a reaction and then get the K expression. But we're going to replace all of those concentrations with our E line instead. All right, so we're going to replace all of that. Well, we will. I actually don't want to do that just quite yet. Because our goal here is to calculate what is Kc. So we actually need numbers here. We can't just put in these expressions. So, the second follow-up question to, okay, when do I have to use an ice table, when do I not, is, when do I make an approximation, when do I not? This is an example where you do not make a approximation. Yeah, so the person up here on the chat says, aren't we told that B is equal to 0.065? Yes, that is the hint that we're going to use to fill in the rest of this ice table, all right? We still need to know how do things change, all right? So we're gonna use that hint that I'm telling you that at equilibrium, B concentration is 0.065. So doesn't that equal X? Yes, that equals X. And that's really useful to us because if that equals X, do we know the concentration of C at equilibrium? Yep, we do. It's the same number. So C concentration equals 0.065 molarity. So then since we know X, we also know the concentration of A. We just got to plug it back in. All right, so notice here we are never making an approximation because we are given a hint to what X is because we're given a hint to that equilibrium line. So you do have to plug in X into that A concentration at equilibrium, so 0.5 minus 2 times 0.065. So that means the A concentration at equilibrium is something like 0.37. All right, so those are the numbers that I am going to plug into my Kc expression. So 0.065 molarity squared, because both B and C are the same, and then A concentration is 0.37 squared. It's squared because the stoich in the balanced chemical equation has a 2 there. And then that will give you K. So Kc is about 0.031. All right. So notice here, I never had to make an approximation because I gave you a hint at the equilibrium line, and that allowed you to calculate X, so you could fill in the rest. This is what I call Sudoku your ice table, because you're given initial conditions, and you're given like a hint to fill in the rest of the table. You know, like when you're playing Sudoku and like you get that one number that you needed and then it just like solves the rest of it for you. Yeah, so that's how I like to think of it. But then I think in the follow-up question, I think we do need to do an approximation. So wait, when we're given pressures to the question instead of concentration, do you use Kc and then convert it to Kp? Yeah, so that's what you would do if, like, for instance, in this question, if I said, okay, calculate Kp, I would actually do everything just how I did it, like, and calculate Kc, and then use that Kp, Kc conversion and delta N to calculate what Kp is, all right, perfect. Okay. So let's do this one. Can I make this go away? I didn't know this is what you guys see. View. Full screen? Is that better? No? I don't know. Okay, all right, so let's do this one. Okay, H2S with an initial pressure of blah is introduced to a container and allowed to reach equilibrium. Calculate the equilibrium pressure of H2 after equilibrium is established, and I give you a Kp. Okay, does this require an ice table? Yes, because I tell you initial concentrations. Since I give you Kp, it makes most sense to work in what unit in this table? In pressures. So, and I give you pressures. So that 1.8 atm goes straight in there, right? So I put 1.8 atm of the reactant in there, and then it's assumed we have no products, nothing else. So I always like to work all ice tables the same. Ask myself, which way does the reaction have to go? Has to go forward, because there's no products. It cannot go backwards. So just like before, what does our change line look like? If we work our way forward, we lose how much reactant? 2x plus x, oh, nope, that's not right. Plus 2x, thank you, and then plus x. So then at equilibrium, we should have a 1 minus 8 minus, whoa, what am I doing? 1.8 minus 2x of that, 2x amount of hydrogen and x amount of that sulfur thing, right? Just like before, the E line goes into your K expression. So in this case, Kp is equal to the pressure of hydrogen at equilibrium squared, the pressure of the sulfur to the 1 power over the pressure of the reactant H2S squared. That is the K expression, where we use pressures instead of molarities here. So when I fill this in, 2.2 times 10 to the negative 6 equals, I'm going to put in those values, but be very careful. It's 2x, but the whole thing is squared, the whole thing. And then the pressure of S2 is just x, so tack on an x at the end. Do not forget that. Over 1.8 minus 2x. Is that it? The whole thing squared, yes, whole thing squared. Okay. All right, this looks real ugly. And I'm not very good at math. So what we're going to do is do an approximation, all right? We're going to do an approximation. This is the idea of our approximation. K is a very small number, has lots of zeros in it. So when you look at this really small k, does this reaction move forward that much? No, because at equilibrium, are you going to find a lot of products? No, because k is really small. So that means x is going to be what? Is it going to be a really big number or a really small number? Small. So when you take 1.8 and subtract a small number, that 1.8 doesn't really change that much, because what's making this math really annoying is this minus 2x in the denominator. This is what makes it a quadratic, and I don't want to solve quadratics on the exam, all right? So what I'm going to assume is this minus 2x is really small. Essentially, I'm going to make the assumption that 1.8 minus 2x is basically the same as 1.8. That's what I'm going to say. Because when I do that, then things get a lot easier. Then this becomes 2x, that whole thing squared, with an x tacked on the end, 1.8, that whole thing squared, right? And then that is a lot easier to solve. That does not require the quadratic at all. I think you just have to do a cubed root. That's it. That's all you have to do, all right? So let's solve this. Okay, this is the approximation that I made. Okay, let's do this math. Okay, but you gotta be real careful. Yes, I made it simpler, but you still have to do the algebra right, because when you have a square on a parentheses, what does this whole thing become? 4x squared, all right? And then there's still an x tacked on the end, so what is the entire thing in my numerator? It is 4x cubed, 4x cubed, over 1.8 squared, all right? So, yeah, so this does not require any quadratic. I'm just going to multiply both sides by 1.8 squared times 1.8 squared, and then I'm going to, I think, divide both sides by 4, because then that cancels, divide both sides by 4. And so when you do that, I think you get something that looks like 1.78 times 10 to the negative 6 equals x cubed. And so you're going to do a cubed root on both sides. And then you get that x is equal to 0.0121 ATM. All right. So, is that our answer? What does the question actually want? Yeah, the equilibrium pressure of what? H2. So what I don't want you to do is like do your ice table, get X, pat yourself on the back, and think you're done, okay? Because X isn't our answer. What is our answer? It is 2x, yes. What do I want? The question wants, what is the hydrogen concentration at equilibrium? That answer is 2x, 2x. So in order to actually report my actual answer, I need to take this number and multiply by 2, all right? So yeah, our answer, the hydrogen concentration at equilibrium, is actually 0.024 ATM or something like that, right? So the question is, how small does K have to be to ignore it? So usually Ks are going to be, if it's something like this, I would say 10 to the negative 4, 5. You want to see negatives. in your K value to ignore it. But I'll show you in the next situation, we can't ignore it, all right? So let's do, yeah, another one, this one. All right, so in this example, we cannot ignore it. So here I have a rigid container, and we initially introduce it with 1 molarity of B and C. So we have to use an ice table because I say initial. So I have 1 molarity of B, 1 molarity of C, and I tell you what Kc is. So that means we have 0A. And I ask you, okay, let it go to equilibrium. What's the concentration of everything at equilibrium? So same process. Which way does the reaction have to go? Reverse. So that means the change line is -x, and then on the reactant side, it's plus 2x. So at equilibrium, I'm going to have a 2x amount of A, a 1 minus x amount of B, and a 1 minus x amount of C. All of this goes into the Kc expression. I'll remind you that it is B concentration, C concentration, A concentration squared. So I'm actually going to put those E values, those expressions in there. So 0.01 equals, B and C are the same, so 1 minus x, that whole thing squared, over 2x, squared. All right? So what some students might try to do is they want to ignore that minus x. But in this case, Kc isn't like that small of a number. And in this example, there's actually something special here, where we have a square on both the top and bottom, the numerator and denominator. So in this case, we call this a perfect square, where if you simply take the square root of both sides, then the square goes away. All right, so 0.01, the square root of 0.01, I think, is that equal to what, 0.1? 0.1, right? And then the squares go away, so now we have 1 minus x over 2x. Does that require the quadratic? Nope, that is just simple algebra. Okay, that you need to practice, all right? Because how do we isolate x and solve for x? We have to move the 2x on the other side, so multiply both sides by 2x, right? So if I do that, then these cancel. 2x times 0.1 is equal to 0.2x, is that right? Equals 1 minus x. Now combine your x's. So what does this become? 1 equals 1.2x. Is that right? Okay, and then we can solve for x easily via division. X equals 0.83. What is this, molarity? Probably, molarity. All right. So notice this was a perfect square. We did not need to do any approximations to get the answer. And an approximation probably would not work because K is not small enough in this case. Oh, and also our reaction's going backwards. So it wouldn't really work there. So do be on the lookout for perfect squares when you have a square in the top and to get rid of that. So is this our answer? No, not necessarily. I ask you what's the equilibrium pressure of everything. So is X the answer to any of these? No. What we need to do is actually plug in those values, the X values into that equilibrium line to get those equilibrium concentrations. So I don't really want to do that right now. All right, so what's this question? Why is on the top, we put it regardless of which direction is going? So in this case, our reaction is going backwards. So since our reaction is going backwards, what a lot of students think is, oh, doesn't that mean I have to flip the reaction? No, you don't have to, because of how equilibrium works. The change line is dictating which way the reaction is going. So because this reaction is moving backwards, we're losing products and gaining reactants. That's absolutely okay with chemical equilibria. Don't think that all reactions have to go forward. Yeah. Oh crap, you're right. It does say pressure. That's because I didn't write it well. You can't, because in order to convert between concentration and pressure, I would need to give you a temperature, a volume, all that stuff. So no, yes, say equilibrium concentration of everything. Thank you. Okay, and then this question, what if the approximation is not multiple choice and it's fill in the blank answer? So remember, our approximations will get us within 1% of the actual answer when we use it correctly. So, you know, all fill in the blank, like numerical input questions, always have a tolerance on it. So if our approximation works, even filling in the blank should get us close enough. What I want you to do is use Wolfram Alpha and put in this entire thing. Right, put in that entire thing, solve it using Wolfram Alpha, then make the approximation and compare the answer. What you'll see when the approximation works is that the two answers will be basically identical, right? When the approximation works very, very well. Because look, what did we calculate for x? 0.01. What is 1.8 minus 2 times 0.01? Basically 1.8. See how this approximation works? If we did the approximation, we got x equals 0.6. 0.6. Would our approximation make sense? No, 0.6 is a really large fraction of 1.8, but 0.01 is a very tiny, tiny fraction of 1.8. So that's why this approximation works. If x was like 0.5 or something, then it would not work. So that is what you need to be kind of looking at when making these approximations. We're going to be doing it a lot in chapter 16. You won't even be thinking about it anymore, but be aware that that's typically what it looks like. Yeah. So the question is, when we manipulate a reaction, why do we square it and not multiply by 2? So let me ask you, what is the equilibrium expression for this, Casey? Of B over A. Okay. What if I doubled the reaction? 2A goes to 2B. Now just look at that reaction. What would Kc be here? A squared. Do you see why? We square things, or if we divided the reaction by 2, we would take the square root, because in K's, coefficients become exponents. Does that help? Okay, all right, perfect. All right. How much more do we have to go? Ooh, a lot. Okay, so let's, I don't want to do 8. Let's do, oh no, yeah, let's do 8. Okay, all right. Okay, the equilibrium constant for this reaction is 4 at this temperature. We make up a system, 1 mole of each in a 4-liter container, and we allow it to reach equilibrium. So when I do the ice table, am I going to put 1 for everything? No, you're going to put what? 0.25, 0.25, 0.25, 0.25, because this is molarity, 1 mole of each in a 4-liter container. Right? So, and I ask you, how will the concentrations of all the species change with time as the system establishes equilibrium? So I need to figure out, which way does this reaction go to achieve equilibrium? So in all the previous questions, it was real easy to figure out whether the reaction went forward or reverse, because there was always something missing. But in this question, everything's kind of equal. So this is where reaction quotient is very important, Q. Q is also products over reactants, but the only difference is that these are not at equilibrium conditions. And so when we compare the magnitude of Q to the magnitude of K, we can predict which way does a reaction have to shift to achieve equilibrium. So what I'm going to do is just plug in these initial values into Q and compare it to K. So our Q or K expression is simply CH4, water, hydrogen cubed, CO. So I'm going to put a bunch of 0.25s in here. So 0.25 squared over 0.25 to the 4th. And I think if I look at my key, this is equal to 16. Right? So I get that Q is equal to 16, and I told you that Kc, the actual equilibrium constant, is 4. So remember, Q, K, whatever, is always products over reactants. So right now, at this moment, Q is 16. So I have too much what right now? Products. That's what I want you to think about. So if you have too much products, which way does the reaction have to go? Reverse. So what is our change line going to look like? It's going to look like minus x, and then hydrogen will be plus 3x, and then CO is plus x. Right, so this reaction went backwards. We consumed products, made reactants, right? So I don't actually want you to solve this for equilibrium concentrations. Instead, I want you to kind of reflect on what does all of this mean, all right? How does the concentration of all the species change as the system establishes equilibrium? Your hydrogen concentration does what? It's going to what? Increase concentration or decrease? Increase. CO also going to increase. CH4 is going to decrease, and then hydrogen's going to decrease. Is there a follow-up here? Yes. Okay. So here's the follow. So I'm just gonna I'm gonna move this down here, just so we can see it again. All right. Complete these following sentences. Once equilibrium is established, the CH4 concentration will be what compared to the CO concentration? Will it be greater than, less than, or equal to? Notice what we are comparing. We're comparing the CO concentration to the CH4 concentration. So which one is going to be greater at equilibrium? CO, yeah, CO is going to be greater, right? Because of the plus X. Okay, once equilibrium is established, how does the hydrogen concentration, so I'm just going to highlight it, compare to the CO concentration? Both of them go up, but which one increases more? Hydrogen, yes, hydrogen. Why? Because of the plus 3x. And then finally, once equilibrium is established, how are the CH4 and water concentrations? They are equal, yes, right? So notice that I can still ask questions, but it doesn't require you to actually solve anything other than just reflect on what that change line means. Okay, good. All right, Chatellier's principle, then I do a demo. All right, consider the following reaction at equilibrium at room temperature. This reaction is an elementary step, meaning that we can just apply chemical equilibrium very easily. Okay, imagine we remove some CO2 from the container. So we're gonna remove this. Okay. What does Le Chatelier predict happens? The reaction moves what, forward or backwards? Backwards, yes, all right, goes backwards. But why? Why does it move backwards? Is it because the reverse reaction speeds up? Okay, let's think about it. Okay, so remember what chemical equilibrium is. It says that the rate of the forward reaction equals the rate of the reverse reaction. So we can make the rate laws for those, right? This is chapter 14. So that means K for the forward reaction times CO concentration, sorry, CO2 concentration squared equals a different rate constant, CO concentration squared, O2 concentration. That is our rate law that dictates chemical equilibrium. So what are we doing to this reaction? We are removing CO2. So if we remove CO2, how does that rate change? It goes down, right? So our forward rate law decreases because we removed some reactant. So the forward reaction slows down. But what about the reverse reaction? What happens to this guy? It stays the same. Why? Because we removed CO2. Is CO2 in the reverse rate law? No, it's not. All right. So the idea here is when we remove like something from the reaction, one of the rate laws slows down. Versus, let's say, let's do this a different way. What if I said we added CO2? what would happen to the equilibrium? We would shift what? Forward. But why would we shift forward? It's because the forward rate, what, increases, decreases, stays the same. Increases, because we increase how much CO2 we have. But does the reverse rate change at all? It does not, because CO2 is not in it, right? So that is what we want to be thinking about with chemical shifts. Le Chatelier's principle just predicts whether it goes left or right, that's it. It does not predict, the reason why. But we're smarter than that, so we can figure out why. Okay, so here, same reaction, but this time I'm heating it. I'm heating it from 300 Kelvin to 800 Kelvin. In which way does the equilibrium shift? So we're heating it. So how Le Chatelier considers heat is just look and see whether the reaction is endo or exothermic. All right, so what is this reaction based on delta H? Endo. So is heat a product or a reactant? Okay. Yeah, when something's exothermic, we like exothermic reactions, right? Because they feel hot to us, because heat is a product. So in an endothermic reaction, it feels cold to us because the reaction literally steals our heat from us. So in an endothermic reaction, heat is a reactant. So when treating Le Chatelier's principle, just draw your triangle heat on the appropriate side and treat it like concentration. Add heat, you're adding a reactant, so the reaction moves forward. Versus you remove heat, you cool down the reaction, you're literally removing a reactant, the reaction moves backwards. So what are we doing? We heat this, so the reaction should go what? Forward, yes, forward. So if the reaction moves forward, how does the value of Kc change? If it moves forward, we make more what? Products, so Kc should get bigger. Yes, the value of Kc gets bigger, all right? So the question is, why is there a shift in the chemical equilibrium? Is because the value of Kc changes. And the reason is because in an endothermic reaction, all right, in an endothermic reaction, the forward activation energy is larger than the reverse activation energy. So the forward rate constant increases more than the reverse rate constant. So that's why the value of Kc increases. Okay, so let's do a demo real quick. Okay, so got a demo here. So sorry, people on Zoom, you can't see. Sorry. So Le Chatelier's principle. So we will do exactly this, predict which way will a reaction shift. So I have a reaction here, a cobalt compound. It's really nice because this compound is colored, so you can clearly see, what's dominating at those conditions, either reactant or product. Okay, I'm just gonna pour some of this out. Okay, all right. So here I have a chemical equilibrium. Cobalt water complex, it is pink, while the cobalt chloride complex is blue, right? So right now I have a bunch of test tubes here that are gonna kind of act as my, they kind of have a mixture of both of them. That's why they're kind of purpley right now. All right, so we're gonna do some different tests on them to see what should happen to the equilibrium. So again, I want to emphasize these test tubes have a mixture of both the pink and the blue stuff in it. So we're going to make some changes and see which compound dominates. All right, so what do we think will happen when we add HCl to this chemical equilibrium? Which way should it go? So HCl has H plus and Cl minus. Does that match anything in our chemical reaction? Cl minus is a what? It's a reactant. So if I add HCl, a reactant, the reaction should move forward. So what should our eyeballs see? We should see it turn blue. Let's hope it turns blue. All right, so I'm gonna add HCl, it's gonna turn a color, let's see. Wow, yeah, see, it's blue. All right, so that's our cobalt chloride compound. All right? Okay, what am I adding next? Water. Water is a what? Product. So which way, what color should it turn? Pink. Okay, water, water. All right, so purple. Yeah, it turned pinker, right? Yep, pink, eh. All right, what are we gonna do next? Hold on, let me go to my iPad. What are we gonna do next? All right, so what we're gonna do now is take 2 test tubes and put one in a hot bath and then one in a cold water bath and see what happens. All right, let's see, cold water bath. All right, do we see what's happening? There's the hot one, it's turning more what? Blue, okay. So in the hot water bath, it's turning blue. In the cold water bath, it is turning more pink, yeah? So where do we think the triangle goes in this reaction? Just guess and check. Just put the triangle somewhere and think, okay, if I heat this reaction, it should turn what, blue? Okay, so where does the triangle go? It is a reactant, yeah. So if I put the triangle as a reactant, this is an endothermic process. Heating it should make it turn blue. And does that match our observation? Heck yes, it does. So again, you can just guess and check, because if I just put the triangle here and said, okay, it's exothermic, heating it should make it turn pink. But that's not what we saw. So that means we should put the triangle in the endothermic spot, all right? So there we go. Ooh, yeah, now it's really, really pink and really blue. Yes, okay, all right. Good, I wanna make sure I have enough time for the other demos. Because I have this LaCroix that I wanna drink. So why don't we just do it right now? Can we just do that demo right now? Okay, all right. So, because we're gonna move on to chapter 16 now, acids and bases. If there's one thing that you need to get into your head is the magic square. The magic square is what relates H plus concentration, OH minus concentration, pH, and POH, right? So, okay. H plus concentration and OH minus concentration, these two values are related to one another by Kw, the autoionization of water. Kw is equal to the product of these two things, H plus and OH minus. This is really useful because Kw is a constant value based upon temperature. So at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14, right? That's very important because if I know H plus concentration at equilibrium, I know hydroxide concentration at equilibrium because both of those numbers multiplied, their product is Kw, 1 times 10 to the negative 14, right? But what you'll see here is that concentration, like H plus and OH minus concentrations, really small numbers, 10 to the negative 6, 10 to the negative 7. Do you like writing scientific notation? No, no one likes to write it. So what we do instead is report it as a pH. P just means negative log. That's all it means. So pH means negative log of H plus concentration. POH means negative log of OH minus concentration. PKW means negative log of KW. P bananas means negative log of bananas. So that's all. So here, if I want to convert H plus to pH, I do negative log H plus concentration. But let's say I gave you a pH and you wanted to go backwards to undo a pH to get back to concentration. H plus concentration is 10 to the negative pH, right? Same thing for hydroxide, right? If I want to convert hydroxide concentration to POH, it's simply negative log hydroxide concentration. But if I wanted to undo it, go back from POH to OH minus concentration, it is simply 10 to the negative POH. So that's to undo the POH, right? Square is almost done. Because how are pH and POH related? They add up to 14. pH plus POH equals 14.00. But this is only good at what temperature? At 25 degrees Celsius. Why? Because that 14 is actually pKw. Right? So if you take negative log of 1 times 10 to the negative 14, it is 14. Right? So this relationship, pH plus POH equals 14, only good at 25 degrees Celsius. But I will point out that 98% of the time we're at 25 degrees Celsius, but there's some instances where we're not, and we give you kW, and you have to account for that. If that's the case, if we're at like a different temperature, the only calculation that is affected by that is this going between H plus and OH minus concentration. So only things that involve kW, like here, are affected if we're at a different temperature. So whether we're at 100 degrees Celsius or 0 degrees Celsius or 25 degrees Celsius, this H plus pH relationship will always be the same. Same thing with OH minus and POH. But what changes is the relationship between H plus and OH minus. That is what changes at different temperatures. Okay, so we'll be using that in a little bit. So let's look at some different acids and bases. So I have a really cool indicator here that tells us whether something is acidic, basic, or neutral. So I'm going to be doing this a lot in that I ask you, what are you putting in your solution? How should your pH react, all right? So right now I have a bunch of this indicator. Green means pH neutral. So right now just pure water is in it. So that's why it is green. It is pH neutral. Okay, maybe we can see a little bit better like that. Okay, you see better? Maybe. So right now this is green is pH neutral. So I'm going to add a little bit of sodium hydroxide. Oh, no, which one am I doing first? HCl. Okay, let's do HCl. Okay, HCl. What do we call that? Hydrochloric acid. It's an acid. So what do you think adding it will do to our pH? It'll go down. So our solution should become acidic. All right, so let's see what color it turns when it is acidic. Okay. Acidic, okay? All right, so we got acidic, green is neutral, and then here in this third one, I'm gonna put sodium hydroxide. What kind of substance is that? That is a base, specifically a strong base. So when I add base to this water, the solution should become pH basic. Yeah, more positive, it should go higher, all right? So it should become basic because we add a base. Okay, let's see what that looks like. Gotta mix you. Oh my gosh. Okay, that is basic, right? So we got acid, we got base, we got neutral. So now I have another reaction here. CO2 plus water gives us H2CO3. Does anyone know what the name of H2CO3 is? It's an acid. CO3 is what anion? Carbonate. So if acetate becomes acetic acid, carbonate becomes carbonic acid. So that's carbonic acid. So carbonic acid is an acid. So when you put it into solution, it should make the solution acidic, right? So as humans, we inhale O2 and we exhale CO2. What do we know about gases? Do they dissolve in solution? Yeah, they do. They do dissolve in solution. All right. That was Henry's law. So let's do this thing. Okay. Oh, I'm wearing white, so this should work. Okay. Can you see? Can you see? Okay. Okay, so my breath is acidic, right? If you color match, right? Isn't it? It's acidic, okay? And the reason is because we exhale CO2, all right? CO2. All right, what other things have CO2 in them that we talked about last midterm? Sparkling water, yes, sparkling water. So the first ingredient for this LaCroix is carbonated water, right? Carbonated water. So what do we think will happen when we put a little bit into this container? It should change it to what? More acidic. So it should turn the orange color. So let's see. So just a little bit. Yep, super acidic, all right? Because there's tons of dissolved CO2 in here, making it bubbly, but also adding to, that acidic flavor. They say don't drink too much soda, it'll dissolve your teeth, right? But then I have something interesting here. So we got, CO2 carbonated beverages, but there's this, other class of beverages that are actually, instead of carbonated, they're nitrogenated instead, right? So there's a lot of like Guinness beer, a lot of stouts and porters. Instead of carbonation, they use nitrogen instead as the gas that propels it through those kegs. So it's not super probably appropriate for me to bring in Guinness. So instead I brought in this Nitro Monster. All right, so this Monster energy drink has nitrogen as the gas inside of it. All right, so nitrogenated water is one of the first ingredients. So will nitrogen make carbonic acid in water? No, it won't. So what do we think will happen when we add a little bit of Monster energy drink to these different indicators? What do you think? I don't know, maybe it'll be basic, who knows? So let's just see. Let's see what happens. Okay, so a little bit of Monster. So it looks like the Monster Nitro energy drink is also acidic. So yes, it's made of nitrogen or whatever. The bubbles are less harsh on your tongue. Let me read you the other ingredients. It's nitrogenated water, sugar, glucose, and then the fourth ingredient is citric acid. Yes, so citric acid is a acid, so it's obviously going to make it acidic. So does anyone want this Monster? Because it'd be a waste. I paid $3 for it. I'm going to put it right here, and anyone can grab it. And someone can have the LaCroix too. I don't really want the LaCroix. Okay, so anyone can just grab it. Okay. Is it good? Can you try it? Have you had it before? Is it good? Does it just taste like a flat? Tangerines, okay. You're taking the LaCroix, right? Yeah. Okay, perfect. All right. Yes. All right, so, okay, we got 12 minutes left. Is there a certain question you want me to do for chapter 16? Okay, I want to use these figures, the last couple, and then we'll work our way backwards. Okay, so this is question 15 on page 10. All right, so use this figure. The department loves these figures. Yeah. So use this figure for the following question. So notice that we have acids on one side and their conjugates on the other side. And what we see here is that the strongest acids are at the top of this chart, but while the strongest bases are conjugates of the weakest acids. So the idea here is the stronger the acid, the crappier its conjugate base is as a base. Versus if you have an acid that's a really crappy acid, its conjugate base is a really good base. And that's what this graph is saying. So we should be able to use this graph to easily tell which substance is the strongest acid. I have 3 substances. These are all acids. So I'm simply going to look at the acid chart and look for these things. So I have HF, I have water, and I have NH4. So clearly, which thing is the strongest acid? HF, because it's highest on the list. Okay, so let's do the same thing for bases. Which thing is the strongest base? Look for them. We have F minus, HPO4 2 minus, so be very careful because the phosphate things show up multiple times, but have different number of hydrogens. And then what else do we have? HS minus, so right there. Okay, so based upon that, which of these substances is the strongest base? HPO4 2 minus. Okay, so that's pretty easy when I give you the full chart, but I don't have to give you the full chart. So let's keep going here. So notice that I have the same 3 substances. So HF was the strongest acid. So which substance, same 3, has the strongest conjugate base? So let's remember, strongest conjugate base is typically we have the weakest acid. So let me draw that better. So the weakest acid, like HA, will have a very weakest acid will have a very good conjugate base. So the conjugate base of HA acid is A minus. So therefore, our answer from before, the strongest acid has the weakest conjugate base. So if we look at this list, water is the weakest acid, so therefore water will have the strongest conjugate base. So then if we look at the follow-up here, the same idea, it's just the weakest of the set, HF, is going to have the strongest conjugate acid. So let's see, strongest conjugate acid would be HF right there, right? Okay. Okay, so these questions are a little easier to navigate just because I give you the whole diagram. So these ones get a little bit trickier here. So only using this figure, answer the following question. Which of these is the strongest base? Notice it's the same thing. So we technically already know the answer, but I want you to use only this chart to answer it. All right, so this chart, yes, it's an acid table, but I didn't make a mistake. We want to use that piece of information that we want the strongest base. So we're going to look for the weakest conjugate acid. Okay, so these are the acids, so we're going to be looking for their conjugates from this list of bases that are given. So if F minus is a base, its conjugate acid is HF. If HPO4 2 minus is a base, its conjugate acid is H2PO4 minus. So tell me, what is the conjugate acid of HS minus? H2S. These are the things you're going to look for on this list, right? So look for those ones. We're looking for HF, we're looking for H2S, and we're looking for H2PO4, because these bases that are actually given, they are on the other side, but we can't see them. HS minus, HPO4 2 minus, right? So based upon this ordering, HF is the strongest acid, but F minus is going to be the crappiest base. So therefore, H2PO4 minus is the weakest acid, so therefore HPO4 2 minus is the strongest base. So see how we got that? We're looking for the conjugates here, right? So it's not a mistake. Don't be like, oh, we can't answer this. Yes, we can. Here, which is the strongest acid? But look, I give you a base chart. So we need to look at these acids that are given and predict what are their conjugate bases. So what that means is these acids will act like acids, rip off a proton, and tell me what is left over after water loses a proton. So after water loses a proton, you are left with OH minus. When NH4 plus loses a proton, or an H plus, what's left? NH3. When HF loses a proton, what's left? F minus. So these conjugates, this is what you're looking for in the table, and then you relate that back to figure out what the strongest acid is. So we have OH minus, NH3, F minus. So are we looking for the strongest base? Nope, we're looking for the weakest base. The weakest base will have the strongest acid. So HF is our answer here, all right? So that's how acids and bases are related to one another. in terms of their conjugates. Conjugate acid-base pair will just differ by 1 H+. So the last type of question is here, also using this chart, but the full chart. So in this question, I have this, now it's a full-blown chemical equation. So like a full-blown acid-base neutralization reaction. So with questions like this, we want to look at where's my acid and where's my base, and how are they reacting? So how we use this chart is recognize that in an acid-base neutralization reaction, your reaction will always favor the weaker acid-base, I guess, combination, I guess I want to say. And the reason is because weaker acids and bases, they are more stable. That's the reason, like energetically. Right? So what we want to notice here is that we have HCl reacting with F-. One of these is an acid, one of these is a base. And on the other side, we have the conjugate acid and conjugate base. So we need to look for those two sets in this table and pick the weaker set. So this is how I like to think about it, right? Just look at one side. All right, let's look at one side. HCl and F-. Which one's the acid and which one's the base? HCl is the acid. It has to be, right? Because it's the only thing with hydrogen, yeah. F-, therefore, is the base. So look for those two things in the appropriate side, all right? So you're gonna look for HCl on the acid side, and you're gonna look for F-. Are you gonna find F- on the base side? No, you wanna find F-, or sorry, you won't find F- on the acid side, but you'll find it on the base side. Right. So I highlighted those. Then notice we have our conjugates on the other side. Cl-, that is our conjugate base, and HF, that is our conjugate acid. So we're gonna highlight these ones too. Where are those on the chart? They're just gonna be opposite of their partners. So you look at the two sets. We have, here are our products, here are our reactants. Which one has the weaker set? The reactants or the products? Yeah, yes, the product. So the product has the weaker base, the product has the weaker acid. So here, this reaction favors the product side, the whatever side that is, right? Is that the right side? Yes. So that's the strategy. You need to find where is the acid, where is the base, and you locate where they are on the table, and you pick the weaker set. So let's just do one more. F- and water. The question is, should we be able to do this without the graph? No. It'd be very difficult to do it without the graph. So, because it's hard enough looking at these, okay, what is my acid and what is my base? F- is the, can F- be an acid? No, there's no H+. So F- has to be your base. Water then has to be your acid, right? So that's what you're gonna look for, all right? I'm gonna highlight them in yellow, my reactants. So F- is my base, water is my acid, and then my conjugates I will highlight in pink, OH- and HF. So which one is the weaker set? This time it's the reactants are the weaker set. So this reaction favors the left side, the reactant side. All right, so we'll end there. Sorry I couldn't get everything in chapter 16, so please refer to the key. Have a great evening. Yep.
I just don't, I'm just a little bit confused.
So